Hello, good evening. Slightly in a different configuration this evening. You're very welcome to join us. Do let me know in the chat whether you can hear everything all right, because I am set up slightly differently, and I know that I might need to move my microphone at times. It's a little bit more experimental this evening, but don't let that put you off. Let me put that there. That might be better. So yes, good evening. You're very welcome to our Erica Synths educational DIY VCO build along. This is what I hope will be the first of a series of live streams where we get together to build the entire series, the entire range of Erica Synths and new educational DIY Eurorack modules. Because what they decided to do was to come up with a simple Eurorack voice that people could build, and while they build it, they can learn how that works. They can learn a bit about circuit design, they can learn about how these things operate, rather than just simply soldering a module together, which is something that I've been doing up until now. So what this evening is, what this live stream is, it's not a tutorial. I'm not telling you what to do. It's a build along where we all try to learn something. Well, I'm trying to learn something. I'm trying to learn more about this, more about circuit design, more about what goes into a Eurorack module. And I wanted to essentially share that experience with you. So hopefully, if you've got this kit already, you can build along and we can sort of enjoy this experience together. If you don't have it yet, then it will give you a good idea as to what it will go through. Now, having not done this before, this being the first of the series, I don't really know how long it's going to take and how much detail we really need to go into, because there's some fantastic materials by oh, hang on, I wrote his name down so I didn't get it wrong. Moritz Klein. He's been working with Erica Synths to put all this together, and he's created some fantastic resources, some great manuals and videos and bits and pieces to help you experience the building of this model to the greatest and fullest extent. Now, we're going to be going through those materials during this video. As I say, this first one's a little bit experimental because I'm not really sure whether it will just take too long to just read through it, or whether we're going to need to skip about a bit. I don't know. Thank you, Jeremy. Yes. So I don't know. We're gonna give it a go. But I mean, I felt it was really important to put forward the idea that I'm doing this for real. I haven't sat down and studied everything first. I haven't gone through it before. I've only opened the box. I haven't even got the front panel out of here yet. So that my experience and our shared experience of this is as realistic as you just having received the pack, opened up the manual and are having a go. That's what we're going to do. If that gets too boring and laborious, well then, you know, maybe I'll have to put a bit more effort into it next time and come a bit more prepared. But this is where we are. So we're going to give that a go. Is that all right with everyone? I'm just going to grab a drink, I think. So let's prepare ourselves for what should hopefully be a very interesting evening. Right, so the first thing we need to do then is look at this manual. So you'll find it on the Erica Synths website. It is also linked in the description of this video if you're on YouTube. And the module that we're talking about this evening is the VCO. Just take this out of here. So ultimately, in the second half of this evening, we're going to be soldering this together, putting on the front panel and the hardware, and we should have a functional voltage controlled oscillator. That's the plan. No, I haven't finished the Deckard's Dream, thanks for asking. It's just up there. We'll get to that. You know, there's more things in life than just building the Deckard's Dream, is what I'd say, and this is one of them. So that's what we're going to get to. But before that, we're going to do stuff on a breadboard, which is exciting. I've not used one of these since I was about 15. So, I don't know. You've got a pint. You know, I was thinking of having a drink, and then I thought, no, it's just going to go far, far worse if I start doing that. Anyway, let's not waste any more time. So let me see if I can remember how to bring all the different bits up. So hopefully that will bring up the manual, and we'll look through it a bit together. Great, so this is the circuit design. Are we supposed to understand this? No, not really, but that's okay. I mean, I think anyone who's interested in electronics will become familiar with the various symbols and bits and pieces over time. But you can certainly probably see in there, like up at the top left, there's 100K, well, that's going to be a resistor. We got with a wiggly line. You see there's underneath where it says course, there's another resistor, 100K, but it's also got an arrow on it. Now that is likely to be a variable resistor because you can move it up and down. In fact, it says, look, 100K, 10K. They're probably related, I should think. Yeah, you can tell that I've done my homework on this. And then in the middle, you've got sort of triangles and stuff. And you see that 1 picofarad, I think that's going to be a capacitor. So this is essentially what we're looking to build. And as I say, you don't need to understand what this is or what this does. But hopefully in the working of this evening, we might pick up an idea. Now the manual is like 50 pages long, which is extraordinary, and there's such good stuff in here. But we're just going to follow through the breadboard stuff, the building of the VCO onto a piece of breadboard to see if we can get it to function and understand what's happening along the way. At the back of the manual, there's lots of information on the individual components, what they are, what they do, and that's all great stuff. But we're not going to spend any time looking at that. You can read those parts at your leisure. We're just going to go through the main bits to create this oscillator. Now it is an analog sawtooth core oscillator. Moritz says it's reasonably accurate, which is nice to know. And he starts off by talking about what an oscillation is. So as I say, let's see if we can go through this together. And if it's just too much, if it's too wordy, then we'll think again. But we'll just follow it through, and hopefully we'll gain something as we go. I don't believe there'll be a physical edition. I mean, it might be made into a book at some point, but you know, you can print it out. It's just a PDF. So oscillation basics then. Right, finger scrolling isn't working so well today. So as I say, get hold of this and you can read it in greater depth, because I may skip around a little bit. So what this is saying is that essentially we have two main properties with electricity that we're able to measure. We have current and we have voltage. And these are being visualized as a pipe filled with water, closed at both ends. So there's no force applied to the water. It's not moving. So we could also say that the pressure of the pipe is at a neutral level. So we're creating an analogy between electricity and water in a pipe. Yeah. So water within a pipe with closed ends is exactly the same as just a piece of wire, because there's nothing going on that's pushing electricity in it, through it, or past it. It's just sitting there in a constant state. However, if we hold a battery to one end of it, then it changes. It's like connecting a water pump to one end of the pipe. And with the other end still closed off, the water pressure will increase as water is being forced into that space. The battery's doing the same to the piece of wire, and the piece of wire would actually get hot, potentially. Is that right? Oh, I don't know. No, it wouldn't. That's not right. Scrap that. See, I mustn't jump ahead. Okay, so that's roughly what's happening to our wire and battery. There's no current flowing, but the voltage inside the wire has been raised by attaching the battery. If we were to turn the water pump off, we can expect to see the pressure inside the pipe return to its original neutral level, and it's the same with the wire. But instead of holding it to the positive terminal, connect it to the negative terminal, and the voltage in the wire would neutralize. So you've got this idea that you have a wire and a battery. You attach the positive to it, and it increases the voltage in the wire. You then connect the negative to it, and it decreases back to neutral. So if you keep swapping that battery over, you're going to get a peak and then a drop and a peak and then a drop. And that is an oscillation. And that's what we think about, or that's what we see when we start looking at waveforms. So if you see the graph there, you've got voltage and you've got time. And so every time the positive is attached to the wire, you're getting this positive voltage level. And then when the negative is attached, you're getting this reducing back to zero. And that's giving you your pulse wave. Could be a square wave if it's very, very regular, or it could just be a pulse. It just depends. It depends on the timing of that. And it's constantly swinging between these two levels. So this is what a pulse wave really is. It's an ideally instant, constant swinging between two fixed voltage levels, where the waveform's height determines the volume, while the wave cycle width determines the frequency, or the pitch. And the same idea applies to all other waveforms. They are just shaped differently. So if we look at our sawtooth, which is what we're trying to generate, you can see that you get that initial on, but then you get a decay and an increased duration of the second phase. So it's no longer straight up, straight down, it's straight up, and then it decays away. So that's what we're going to try to achieve with our oscillator. Don't worry, we're going to get to doing stuff in a minute, okay? Right, so let's look at the oscillator core. So at the center of it all, we're just using 4 components: a resistor, a capacitor, a diode, and a Schmitt trigger inverter, which sounds very exciting. And that's all that's needed if you just want a single frequency sawtooth oscillation. So what's happening when we turn this thing on? Well, if we start looking at the central point in the schematic, which I assume is that dot, I'm going for the dot in the middle as opposed to the Schmitt trigger, which is a bit more, I don't know. Yeah, go for the dot, I think. So initially we'll measure no voltage at all because the capacitor is empty and nothing's passing through our diode. Now a diode, if you're not aware, you see the triangle with the line on its nose. Well, a diode will only let current flow in one direction, sort of through the triangle, like the way that it's pointing. If it's going the other way around, it won't go through it the other way. So a diode only lets it go through one way, the way that it's pointing, okay? So because there's no voltage at all because the capacitor is empty and nothing's passing through the diode yet, that means that the Schmitt trigger, the sensor, will tell its output to start pushing out current. That's interesting. I don't know anything about a Schmitt trigger, but that apparently is what it does. Since we're below the lower input threshold, okay, so now we have a flow from the output. So the triangle, the big triangle with a circle on the front, is pushing out current. and it's going up round the corner through the diode, and then it comes to that dot in the middle, and it has to decide where to go. Should it go through the resistor, which is on the left, the wiggly line, down to ground, or into the capacitor? Now, a capacitor stores current, whereas a resistor will reduce it down to earth. Oh, look, Moritz is in the chat, which is awesome. Well, that's lovely of you to pop in, mate. That's just fantastic. I hope I don't make a complete hash of your thing here. I'm I'm really chuffed that you're there. So I am doing my best, mate, to sort of read through and interpret what you're saying, because it's always good to do that. It'll get exciting in a minute. This is just getting through the basics. Okay, but what exactly do it mean by we saying electricity is going to ground? Well, to stay with our analogy, imagine that ground is basically what's behind the opening in our pipe system. It's a huge natural pressure reservoir into which our water can be released. This means that through this opening, our water can leave the system for good. And it depends on the resistor value or the narrowness of that drain pipe and the voltage before it. With a capacitor path, it's a little bit more complicated. If it's completely empty, it is virtually indistinguishable from a straight connection to ground. The balloon is empty. Ooh, got a balloon. And you can dump water into it effortlessly at first, but as it fills up, it starts to push back. It gets harder and harder to push more water in until the pressure is not strong enough anymore. And now the capacitor looks like a dead end, as if the pipe just straight closed at this point. So that's interesting. So your capacitor is filling up with stuff, and the pushback or the resistance increases as it does so. So it starts off by being just a straight piece of wire to being something that's completely blocked. So what happens from the current coming from the Schmitt trigger? Well, since our capacitor is empty, filling it up will be the path of least resistance. So pretty much everything will flow into there. But while the capacitor is filling up, the voltage at our central point will increase rapidly, because now the only way out is through the resistor, where just a very limited amount of current can leave our system. The lion's share is going to accumulate, raising the voltage. So what it's saying is, as the capacitor fills up, it gets harder for stuff to go in there, but it's also hard to go out through the resistor, because that is resisting the flow, not stopping it completely. And so the pressure is increasing, if we're talking about the water analogy, which is the voltage. The voltage is increasing because the current is being restricted. But that increase in voltage is also registered by the Schmitt trigger's input. So as a reaction, the output will drop down to 0 volts once the capacitor is charged and the voltage passes the upper input threshold. So as that voltage is increasing behind the Schmitt trigger, if we go back to our little diagram, as the voltage is increasing there at that dot where everything is happening, it hits a threshold that the Schmitt trigger turns off and is no longer feeding the system. See, that's really interesting. This is all new to me. So, you know, I'm learning at the same time as hopefully you are a little bit. Now, where was I? Okay. So no additional current is being forced through the diode, which in turn means that our capacitor has no opposing force anymore. So we've essentially stopped pushing water into it, and so our balloon will push its contents back into the system. So the capacitor will now dump the current back into the circuit. Can't go back into the Schmitt trigger's output because the diode is blocking that. Can't go back round that system. The diode only lets it go through one way, yeah? There's only one pathway, and that's through the resistor to ground. But because that resistor is restricting the amount of current that can pass, our capacitor won't discharge instantly. It will take some time. So on the voltage graph, you'll see the slow decline. And then it will start all over again. Let's go back to our diagram. So the I think, let me try to summarize this. So I think your triangle, your Smith trigger, the triangle, the circle, kicks out a bunch of current. It goes through the diode, hits our middle dot point here, where it doesn't want to go down the resistor because that's hard. So instead it goes into the capacitor, which then fills up. And that happens really, really quickly. As that happens, the voltage at that dot increases so that the Smith trigger can understand that voltage there and go, oh, it's too high, I'd better stop. That's what the Smith trigger does. It's a clever little piece of circuitry which does all that all by itself without us having to think about it. So that turns off the tap, so there's no longer stuff going through here, and all the current is in the capacitor. The capacitor then, with no longer having anything coming into it, can let the whole stuff back out again, can discharge. And because of the resistor, it's actually quite hard to do it, so it doesn't dissipate anywhere near as quickly as it came in. And that is going to give us this graph where we have this more or less instantaneous voltage raise as the capacitor is filled, and then the slow release as all that current pours out of the capacitor back to zero. And that gives us our flipping sawtooth. Look at that. Now, of course, in this little diagram, there's no like audio output or anything like that. This is just trying to understand the basics of how that waveform is created with this, you know, relatively simple little circuit. That's pretty awesome, that is. Right, let's build the thing. Have I got that far yet? Yeah, no, I think we are. We're going to do that. That's exciting. Right. So Moritz suggests that you get a breadboard. That's what I've done. I did read that much beforehand at most. And I've also had a quick look at his beginner's guide to breadboards, which was also useful. You'll find a link to it here, which is in the manual. Now, come on. Oh, okay. All right. Okay. So we're going to start building this on a breadboard, which means I need to change the view a little bit. Do I need to do that now? Yeah, possibly. So if you have access to this manual, do keep it open perhaps in another tab and refer to it, because I'm going to make it a bit smaller on screen now so that you can see what the heck is going on here. I'm going to need to move that thing. Just a second. I got that right. Right, where am I? Right, I'm just making sure that we're all seeing the right thing. Yeah, I think so. Okay, hopefully I'll get all this in the right place and we'll be able to see what is going on. Yeah? So, in this kit you'll find everything you need. So maybe that's a good start. Let's do some of that before we start putting things in the breadboard. Let's lay out the components so we can see them. Now the breadboard I got separately, as the same with this and some other wires and bits and pieces. Hopefully I've got 2 of those. Yes, I do. Get to those in a minute. But let's just have a look at the kit itself. This is all the hardware bits and pieces, which we're not going to get to just yet. Let's have a look at the main components. Okay, we've got a load of stuff. So we have resistors. That's these fellas. Look like sort of little globs of blue tack on a wire. There's a few of those. Actually, there's a lot. You could probably say that for every component. They're all blobs of blue tack, really, on wires. So resistors are very popular in circuits, I find. Those are diodes, those things there. Oh, there's my chip. and a chip holder. Couple more resistors. That's a nice fat electrolytic capacitor. That's some kind of three-legged thing. Probably a what's it? Oh, look, there's another chip. Okay, got those bits. Now those are pretty. Oh, I like those. There's some sort of capacitor, I think. So are these white things. Again, I think these things will become clear as we build it. There's a trim for doing some adjustments. Another three-legged thing. A couple more resistors. A couple more of these gobby sort of capacitors. And that's the main stuff. Oh, there's one here. Oh, look, there's one rolled away over there. So these are the things we're going to probably be using on our breadboard to start with in order to construct our circuit. So these bits here, the PCB, we'll be using that in a bit. Good Lord, it's already 8:30, but we are getting to the breadboard now. So I'm going to put these bits to one side and focus on whatever it is that's happening next. Right, so in this kit you'll find everything you need. You need a 2.2 nanofarad capacitor. Which one's that then? And a 100k ohm resistor. A small signal diode. And for the Smith trigger we'll be using the 40106 IC, which is 6 of those in one single chip. Okay, so we're going to need to track these bits down. Right. Okay, so all right. Well, my question, I guess, at this point is, how do we know which bits they are? Am I going to need to look? Okay, let's see if it says anything here. No, right. Okay. If I hop over to the build document at the end, maybe that will give us a bit more information on that. Heck. Okay, that got complicated quickly. Right. Okay, right. Let's go back to page 7 where we were on. Okay, so we've been told to bring together a couple of components, but it doesn't actually show us what they are. So we're going to have to use a little bit of intuition, because there's nothing to tell me what any of these things are. Let me get my glasses. So I can see. Okay, so I've got these little fellas, which are 104. I'm looking for a 22 nanofarad. It's a 47 nanofarad. 47. See, the big fat ones, they tell you what they are. These other ones, they do not. The white one, I'm just going to have to Google it, I guess. That's slightly frustrating. 104. So those are looking to be all the same. So it's probably those. Okay, so who's got your resistance calculator out? 2.2 is one of the white ones. Just about make out the writing. Which one are the white ones? What one of these? Oh yeah, look, 2.2, J100. That big, this one you think? This one? You reckon it could be that one? Because this, I think I'm right in saying that the square ones are the film capacitors. These are glob capacitors. And these are electrolytic, which make me sound like I know what I'm talking about. So yeah, no, that does say 2N2 on there, which is a 2.2, which is how they write 2.2 nanofarad, as in 2N2. That could be it. 100 kilo resistor. All right, anyone good on the... I don't think any of these are written on. Anyone good on the bands of stuff? Well, I mean, I guess if I'm being really kind, I'm saying that that this is forcing you to find this out, as opposed to being taking you by the hand. But you're not necessarily going to have a multimeter. That's a slight frustration, I would say. If you're a beginner at this, then you might not want to get a multimeter straight away, so you don't know whether you're going to like or enjoy doing this. I mean, a breadboard's a tenner, but a multimeter is a little bit more than that. So I think having the resistor values written out already in the manual would have been a really nice, really helpful thing. Anyway, 100 kiloohm is probably this one because they're very common. Obviously, I can go and get the sheet on the things. There we go. See that? That's what I thought. See, I am learning something. So these are the brown, orange, black, black, brown, or it could be brown, black, black, orange, brown, depending on which way up you are, which is probably important. See, it's at points like this that I think it becomes obvious how much detail and how little many people will know. So these are 100k. I'm going to write it on me piece of what's it. 100k. Good. Right. Put those to one side for a minute. I'm just gonna, while I've got me what's it open, me multimeter, I'm going to measure these ones. So all I'm doing is put it on 2 legs. That is 1k nearest, damn it. So I'm going to write that on. Now it may be that later in the manual we will find all of this written out for us, because it's useful to have a bill of materials. By a bill of materials I mean just a list which tells you how many you have of each thing, because that helps you identify stuff. Black, black, yellow, golden. Are you talking about your beer, Ken? Look at the appendix. I can't pay attention to everything, Robin, with the greatest of respect. So, all right, let's have a look at the appendix, see what it says. I was in there a moment ago, and I didn't really see that. All right, so the module assembly appendix, before we start building, see, I don't want to get to this point. I want to get to this point later when I build the module. At this point, I'm just building on the breadboard, and I just need to identify the components I want to put in the breadboard. Do you see what I'm saying? Yeah? Anyway. I don't see what the appendix is giving me at the moment. It's giving me a schematic, which is fine, but if I'm a beginner, that's not a great deal of use to me at the moment. What I'm looking for the components appendix. Okay, there's another appendix. I do beg your pardon. Multimeters, tools appendix. Bipolar junction transistors, op-amps, AC coupling, potentiometers, voltage dividers, capacitors, resistors. Okay, components. Yeah, resistors. Okay, I'm sorry, I don't mean to whine. This is the components appendix, right? Yeah, but I'm still not getting a bill of materials. It's still not telling me how many 100k resistors I should have. Or, okay, it's bit back capacitors. There's ceramic. Okay, film capacitors are the boxy ones. So that's good. Okay, so that does confirm that this is the 2.2 that we want. These ones are called ceramic. That's right. That's the word I've been after. Thank you. It doesn't have a bomb. Okay. I think that's a mistake. Never mind. So I'm not going to find any help here. Let's go back to page 7. Let's just work it out. What else am I supposed to do? So that's cool. So what was I doing? I was measuring resistors. Let's just finish off that job because that's going to be helpful later on. So this one here. Ooh, that's a 1 meg. That fella, that's a big one. That's a 1. Can I write an M on there? Okay, so 1M. $33K. They're magnifiers on my head because my eyes are rubbish. 47K. Oh, starting to heat up in here now. Oh, it doesn't really know what that one is. 10 ohm. Come on. Come on. 10 ohm. $68K. Is that another 1 meg? Nearly there, come on. Keep going. Okay. And 14k, right. Am I going to be able to see that? No, I'll probably have to be measuring it again. Not to worry. So I need, after all that, a 100 kilo ohm resistor, which is one of these fellas here. Which I've got as brown, black, black, orange, brown. That's the fella. So that's the resistor I need. That's the capacitor that I need. Is that all I need? Now we need the 1N4148. So that's going to be one of these. Or is it? Yeah, no, it is. It's going to be a chip. Oh, gee whiz, flipping G's. Okay, 40106. 40106. Yes, good Lord, it's written on there. Okay. So we'll be using a 40106 IC. Okay. I haven't, oh, the other one was a diode. Right, so we're using this thing here. Let's take that out. Come on. Come on, hold it together, man. Hold it together. Now, for the diodes, I seem to have a choice of 2. Thick one or thin one? I can't read that. Again, if there was a bomb, I could know the difference because it would list 2 of one and 1 of another. God damn it. It's the red one, says Corey. All right, go for that then. See, this is why I keep you around. Because doing this by myself, I would just be driving myself nuts at this point. Okay, good. So, we got the little bits we needed together. Now, what I would like to see in a manual, if it's all right, if nobody minds me saying, because, you know, here I am doing it and stuff, is like a picture of that, you know, and it should say, find these bits. This is this, this is this, this is this, this is the other, because this is the first time you're handling components, potentially. This is what you're looking for. Now, we're talking about this fella here. And chips or ICs have an orientation. They have a cutout which tends to show you where pin 1 is. So if we're looking at the manual where it's got the drawing of it, apparently you've got a positive voltage on that front leg. You've got a ground on that bottom left leg. And in between you've got 6 SMET triggers which go just in pairs of legs, which is beautiful. What a lovely thing. I mean, chips are always a mysterious entity. It's just this slab of stuff that contains, you know, unknown functionality. And we know now that this 40106 is a bunch of SMIT triggers. And we know that SMIT triggers can be used to create sawtooth waves. Fantastic. So to get the chip to operate, we need to connect pin 14. Okay, marked there. What's it, 7 aside? Is that pin 14? So, okay, if my memory serves, in that case it goes 1 to 7 and then 8 to 14 up the other side. It sort of goes down and up as opposed to across or down and down. So this up here is pin 14 is what it's saying. Because pin 7, which is down here, goes to ground. Okay, so pin 14 needs to go to the positive, while pin 7 needs to be tied to the negative terminal of our battery. And then we can choose any of the 6 inverters to be the one we're working with. There's a catch though. We need to connect all the unused inputs to ground. Okay, otherwise they might pick up static noise and make the inverter we use act somewhat unpredictably. Okay, so here's how you could set everything up. For the diode, orientation is important. If you look closely, you'll notice a thick black line. Thick black line. That corresponds to the line in the diode symbol. So if you're looking at this diode here, my finger behind it so you can see it, it means that current can flow this way but can't come the other way. Yeah. For the capacitor and resistor, this sort of capacitor, other capacitors it does matter, but for this one it doesn't matter. Because it's non-polarized, and there's the breadboard. So I think what we are going to have to do at this point is actually plug things into the breadboard. So because the next line says if you've connected everything as shown. So let's go for this. Can I? Well, the surface is just not responding brilliantly today, but I'm asking it to do quite a few things. So I'm just going to bring this up bigger. And let's see whether we can work this out. Sorry, juddering things. Is the audio cutting out? I'm not monitoring the audio myself, so you'll have to tell me if it is. Seems fine to you, Bill? Okay, cool. Okay. Depends on what you're watching on. I mean, I'm assuming everyone's on YouTube. Who knows? Anyway, breadboard. Bang. So I got this off Amazon. Cost about a tenner. And what I understand from Moritz's awesome breadboard introduction video is that you have these lines along here, these 2 rows here connect this way, as do these, whereas the ones in the middle connect this way, but not across this middle bit. So those 5 are connected, these 5 are connected. This is a gap between it, which will stop everything bad from happening. And so the idea is that if you want to connect 2 things together, you jam something in it like that, and you want to connect that to something, I can connect it on the same one, and it connects up because it's on the same row. Yeah, simples. Whereas here, that all goes along, and you use these top and bottom ones for power, which we'll get to in a minute. But first of all, we probably need to place the chip because everything revolves around it. Now, according to the manual, this goes across the big divide in the center. Doesn't really matter whereabouts you put it because all we need is enough space to place your components. So stick it somewhere in the middle. Maybe put it on a one that makes sense. Okay, so this is not going to fit perfectly. Now I have a handy tool which allows me to squash the legs of an IC so that it fits, because if you sort of over push it, you're going to end up bending a leg. Now if you don't have that tool, the way that I've done it is just to rock it a little bit. So you put the legs flat. You see what I'm doing there? Can you get a little bit of shadow on it? I sort of put it down on its side, and without pushing down on the top legs, I just rock it a little bit just to bend the legs in a tiny bit, then turn it over and do the same, and then hopefully that'll then drop in there a little bit nicer. Almost, yeah, see, there it goes, there it goes. Oh, that's not that's not very flat. Oh, I blew, oh, there we go. Bit of pressure, it's in, it's good. Okay, got me little nodule pointing that way like it is on the picture. Good. Then let's see what we've got. So we've got a 2N2 that looks like it goes over this pin here, which is pin 7, and goes to pin 5. Let's try that out. Yeah, squeeze the legs like a caveman. Nice. So that's going in there. Look at that. That's brilliant. See, it's upside down. Now, it doesn't matter. I just like to have all the writing the same way. No, that was upside down now. It was the right way to start with. Oh, I'm losing it. Okay, good. Now, let's put in our resistor. Our resistor, let's bend our legs to start with, is going to go to the positive rail and to the same end, because it needs to be connected to that capacitor. So the capacitor is being, hang on, let's just check our thing here. So the capacitor has gone to ground on one leg, and it's gone to, if you can see this, the output. No, it's connected, that's right, because okay, let's think back to our original Schmitt trigger diagram. The nose of the Schmitt trigger has to go to the diode. We haven't put that in yet. But the capacitor goes to the back of the Schmitt trigger, because that's where that voltage was being created, which turned the Schmitt trigger off. So because it's going up to pin 765, that is the back of that Schmitt trigger. And this other leg is going to ground on pin 7. Right, so the resistor also needs to connect to the capacitor, and therefore the back of the Schmitt trigger. And it needs to go, come back, where are you? Here you are. And it's going to the positive. All right, I don't fully grasp that, but I suppose that must be right. I don't know. Thought it was going to ground. Wouldn't ground be the negative? Don't know. All right, let's keep on going anyway. I'm just following the instructions. So the diode then needs to allow stuff to come out of the nose of the Schmitt trigger, which is on pin 6, and go to the capacitor and the resistor. So that's the way round it needs to be. It needs to have the black stripe on the same, that, you know, the leg nearest the black stripe being in the same place as the resistor and capacitor. Now my resistor is too far up, so I'm going to bring it down a little bit in there, and this comes out of pin 6 and goes into pin 5 like that. Good Lord, it's nearly 9 o'clock. Oh dear, no, I should have started at 7. Right, good. So those are the 4 components that we were talking about. Those are in place. And like in our diagram, I'm sorry to keep going back to this, but I just need to keep reconfirming some things in order to understand it. And my little Surface Go here is not coping very well. So as we saw at the back of the Schmitt trigger, which is on pin 5, it needs to connect to both the capacitor, to the front end of the diode, and one end of the resistor. Then the capacitor goes to ground. The resistor I also thought would go to ground, but it doesn't. But I guess it needs to get power from somewhere. So that's, I guess, why that's going to this thing here. But maybe we'll read about that in a minute. I don't know. So the front end is coming through the front of that, goes through into the capacitor resistor, and that all works. Great. I've got that, I think. Whoop. Now there's a few other connections have been made using jumpers. Now I don't have kind of like neat ones like the ones that oh, they suggested. I've got sort of a ridiculous pack of lots of huge ones, but never mind. They'll work. There's my clippers. So this is what my jumpers look like. Enormous, great big things. But never mind. They're sort of like what comes off a Korg Volca. So going back to our breadboard. So I need to have ground, which is pin 7, attached again to what looks like positive. I need a bunch of these. I've then got to connect the inputs of the Smith triggers, it said. So pin 3, 1, 2, 3. That also goes to ground. Although it's not going direct. I've got it in the gap. That's annoying. It doesn't make any difference. It doesn't have to be completely straight because these and these are completely separate. So pin 1 also goes to there. Now over here, I've got a short between, so that's 8, 9, 10, 11, 9 and 11. Come on, how many of these do I need? Okay, and I've got that same pin here going out to the positive on there, and I've got 13 and 14 doing the same. 13 and 14. Coolio. I haven't built on a breadboard since, as I say, since I was about 15. He's going to get his power backwards. Why is that? Yeah, no, I definitely feel like I'm making a bomb. Breadboard is upside down. Is it? In what way is my breadboard upside down? That's interesting. See, it's a good job I was asking the right questions. I didn't know there was an orientation on a breadboard. And the interesting thing is that the numbers on here, see those numbers, 5, 10, 15, 20, they are the same as what we see on here. So in respect of the numbers being written on the board, it's identical to the one on the screen. However, these, positive and negatives, are back to front. So what I was saying earlier about the resistor going into ground, not into positive, is absolutely right. Cool. See, this is why this sort of thing is really interesting, because yeah, with the greatest of respect to all of those wonderful kit makers out there, it's not until you give a kit to someone who actually follows the instructions rather than, you know, knowing what it is, knowing how to do it beforehand. Do you see what I mean? That you really come to understand whether instructions work or not. I mean, everybody gets through it in the end. I'll get through it in the end because it won't work, and then I'll check it and check it again, and finally you'll find out where the problem lies. But isn't that interesting how the flipping thing is completely upside down? So what do? Do it like this and then the numbers are backwards? I suppose so. Isn't that interesting? So what I can do is just transfer all of that across to here. I think that's, or I could, yeah, that's the easiest way to do it. I just happen to have two, you see. Oh my goodness me. So let's what should we do? Let's take the chip out first. Can I get the chip out easily? Because there's a danger of bending those things. I think the chances of us actually getting to soldering this tonight are pretty slim. Now I did have next Wednesday nothing going on, so maybe we'll just do the breadboarding tonight and do the actual build next Wednesday. Maybe that's the answer. Or maybe I don't live stream it. But no, live streaming is good. I like that. I like that. I like the fact that we could be doing this together. Right. So now I've got this the right way round. So I've got negative at the top, positive beneath. Does it matter? No, probably not. Long as you know which rail is which and that you're going to connect it together right and you're using some kind of level of consistency. So the fact that these numbers are now backwards compared to what's on the screen, again, doesn't matter. They're just there for reference. It's not important. What's more important is that I get this power right. So if I don't change this, I'm just going to mess it up because I'm going to follow the instructions and my board's not going to be quite right and it's going to go bad. So move this over to here. So this ground here is actually now going to go to ground. The negative. The capacitor goes back into there. The diode goes in the 1 and 2. The resistor now goes to ground, goes to negative. These two were that pin and that pin. These ones are pin 3. Pin 1. This also, okay, so this one goes to negative. This on pin 13 goes to negative, but this last one goes to positive. And what we might do, just for fun, is use a red cable. So pin 14 rather, goes onto the positive rail. This one is again to negative. All right, back to where I was. Get rid of that one. Da, 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 as if it never happened. Right, any comments at this point? Oh dear. I hope this isn't Goldfinger. That doesn't go well, I don't think. I don't have the special watch for deflecting the laser. Right, okay. Flipping heck. Right, did that. Good. Come on, little surface. So, the circuit, apparently, if you've connected everything, should already be oscillating. Though I haven't connected a battery at this point. Okay, so well, he mentions a battery. So if you've connected everything shown here, the circuit should already be oscillating. But what good is an oscillation if you can't hear it? Yes. So let's figure out how do we connect it to a sound system or headphones, whatever you prefer. You might be tempted just to attach an audio socket where the diode, capacitor and resistor and Smith trigger inverter meet. And that's going in the right direction, but it won't work because if you connect something to it, that's this space here right in the middle. Everything will just go shooting off down the audio socket because that becomes the place of least resistance. So that's not how it's going to work. And our capacitor will never get charged because all the current is going through the jack, so it's not going to happen. Because we are tampering with the oscillator's core structure. Interesting, okay. So to avoid that, we need to use a buffer. Buffers also work with voltage sensors. They use them to simply mirror or copy the voltage levels so that they copy the voltage levels that they detect. Okay, so it's like seeing something and then reflecting it over the other side of something, like a portal. Got it, right. Since no current is flowing into the sensors, they're not interfering with what's going on. It's just kind of like a mirror. That's why they're perfect for our problem here. With a buffer, we can leave our oscillator structurally intact and working while still being able to listen in with our sound system. Hold your ear really close to the breadboard, somebody says. Yes. So to build a buffer, we're going to use an op-amp, like you see in this schematic. So that's what those triangles are that we saw earlier on up in the circuit diagram. Triangles are op-amps, I think. So here's a pin out for the TL074. Right, so that's our other chip. Look at this. TL074, that's what that says on. So with the 40106 we had to power and a ground connector, but with the TL074 there's power and a negative power. Ooh, what's up with that? Well, the thing about voltage is that they are always just relative. If we talk about a 9-volt battery, all we really know is that the voltage difference between the two terminals is going to be 9 volts. So what we're basically doing here is that we're picking a voltage level to call 0 and then measure everything relative to that. But this means that 0 volts doesn't necessarily mean no voltage at all. And that's where negative voltages come into play. Because by our definition, any voltage level below the one we've picked to be 0 must be below 0 and therefore negative. Right, okay. So having a positive, a ground and a negative rail is really just having 3 distinct voltage levels to work with. Okay, yeah, all right, yeah, okay, interesting. Okay, but why is that necessary for our buffer? Well, it's mostly to prevent distortion. Op-amp buffers do just fine when they have to copy voltage levels that are comfortably in between their positive and negative supply rails. But if those voltage levels get close to those rails, the buffer can't accurately reproduce them anymore. So while we could just hook our chip up to the positive and ground rails, we should instead use positive and negative rails just to provide it with enough headroom and prevent distortion outright. Clear as mud, that bit, but that's okay. I'm just going to go with it. Okay, there's learning going on. Something's going into my head somewhere. Right. If you have a dual power supply, this is not a problem. Well, look at that. Look, I've got 2 batteries here. Fantastic. But if you want to use batteries instead, it's doable with 2 of them, which is just what I thought he said. So what's a dual power supply then? Don't know. Anyway, so we're using 2 batteries. So the positive terminal of the right battery becomes your +9. The negative terminal on the right one is now your -9. And the other 2 combine to become your new ground, because you take a positive and a negative and it cancels each other out to become ground. And now you've got a minus and a +9 volts. All right, that's genius, that is. Okay, so can we just set that up? Well, we could, but we might still get a distorted signal. to avoid that, we still need to install a coupling capacitor. In order to understand why that's necessary, we have to talk a bit about offset voltages. Okay. There's a lot goes into this. So remember how we said that electrical oscillations are just swings between two voltage levels? The thing about that is that those voltage levels could be high up above the 0 volt line or way down below it in the negatives. Doesn't matter, you still have the same oscillation and waveform, but its center is shifted either upwards or downwards. Normally with audio signals, the center would be 0 volts, but the two oscillations in our graph have what we call an offset voltage of +5 and -5. Okay, I can see that. Look at the graph for our oscillator core again, it's also off-center. That's not an ideal, that is not ideal for audio signals because it might cause the amplifier to distort the sound. So what we need to do is remove any offset from our oscillation. Thankfully, it's really easy. We just need two components, a capacitor and a resistor. These will allow us to AC coupling, good lord, and therefore remove the offset voltage from the oscillator's signal. And it works because the capacitor only lets changes in voltage pass through, but blocks constant currents. So AC coupling, we know a bit about this through AC and DC coupling when we're trying to move audio and CV signals through an audio interface. But in this case, we are AC coupling it in order to remove that DC offset. See, those are words that I've heard before in relation to DC and AC coupling with signal modulation. How interesting. Right, so something else is going on here. If you now hook up your oscilloscope, oh bollocks, I don't have an oscilloscope. Do you have an oscilloscope? Anyone got an oscilloscope? Oh, arse. Well, right, we're just going to have to assume. I mean, as it is, I still haven't plugged any batteries in because the manual hasn't really told me to. And I'm kind of a stickler for following the instructions as best I can. But what we'll do, we'll follow this breadboard, see where we get to. There'll come a point when we can actually listen to it. And at that point, if I haven't been told to plug in a power thing, then I will at that point, perhaps. Let's see. Right. This is hard. Okay, so that's not going to happen then. All right. Okay. Right, so we are getting to the point where we're going to hear this. So I would say that if you haven't gone to look at Moritz's breadboard introduction YouTube video, do go and have a look at that because it does talk about these things. And I kind of think that he's assuming that you've gone there so that you are already happy to plug in the batteries and that sort of thing. I think it would be really good to talk about the batteries in here by actually marking on the diagram that they are connected. I think that's important because honestly, the breadboard on the manual isn't telling me where to plug in the battery. It's making the assumption that I know where to plug in the battery. I kind of do because I have seen that video, although I can't exactly remember now, but you know, the big assumption one makes is that you know how to plug these onto a battery and you know that red and black are positive and negative. So those through those assumptions I can make that work. How exactly I plug this one into this one? Oh, I do it. Oh, I remember how I do it. Okay, I'll do that in a second. I'm going to put the other components in before I put the batteries in. I'm going to come to the batteries last. And while I'm doing this bit, you can all tell me in the thing how I'm supposed to do it once I get there. Okay, good. So what I want to do is now mirror what's on the manual onto my breadboard. So we're adding this chip, this fella here. So again, I'm just going to give it a little rock on both sides. Just bend it in a little bit. Okay. So this time around, it's pointing the opposite direction. So its little nodule is pointing this way. I'm going to squeeze that in there. Doesn't matter where it goes, just as long as your bits and pieces are long enough, and mine are plenty long enough. Right. So there was something else that was required. Which was a so that's the battery bit, the offset. Need two components, a capacitor and a resistor. Okay. So, okay, 100k resistor, I think that says. Again, I'd really strongly advise you to specify exactly which resistor. And then looks like a 1 nano. I mean, I guess that's this one, is it? I mean, this doesn't. I mean, it looks like a square one, like the other one. Doo-ba-doo-ba-doo-doo-doo-doo. Okay. Right. Well, let's do something easy first. Let's do. So those are going to the outside one. Those are going to the negative one. This, which is pin, just going to make this slightly larger. So this is the fourth one along. 1, 2, 3, 4. That's going to a positive. Okay. Pins, of course it isn't pin 1 and 2 because pin 1 is here. So that's 1, 2, 3, 7. So this is pin 8 and 9. Get pinned together. Pin 8 also goes over here out of the way. And I have a pin between. Can't see. So I need to fit a cable in between the legs of that capacitor, diode and resistor, all on that line. So I've got one going in there, and that's coming out to pin 8, 9, 10 on here, which is the third one up. 1, 2, 3 here. Okay, keep going, keep going. Another one on the fourth one along. 2, 3, 4. Now there's something here which unfortunately is bothering me at the moment, and that's this thing. It says negative rail, big capitals, with an arrow pointing to the positive rail. I don't know what to make of that. Does anybody else know what to make of that? So where it says in big writing, negative rail, do you see that on the, you can see that on the screen. What is that pointing at? Is it pointing at the positive rail that I probably would have plugged my battery into, although I don't know where to plug my battery? And is that now a negative rail? And what does that mean? Yeah. Okay, so there's some action in the chat that's talking about that. Okay, I'll just come back to that in a second then, because I'll be getting my battery in shortly. So, oh right, so I've done that, I've done that one, done the little one there. Then over here, this, I think this is the film, the other film. I think this is the 1 pico. I don't know. I'm assuming that it is, because the rest I think is something else. I don't know. I'm going to have to Google it, right? On this flipping keyboard. So what is this called? IJ63. IJ63 capacitor. Okay. So yeah. An IJ63 capacitor. I don't bloody know. God darn it. Right, well I'm just gonna, because it's a block on the manual, I'm just gonna assume that this is the one and just plug the bloody thing in. Right, so that goes in there to there. Now that fills up a bit of space because it's a bit chunky, but it goes along three lines, and then the 100k resistor goes off one leg back into the negative again. Then they've got a little short, or not a short, but a connector to go from that leg to there. Does it matter? I don't know. Maybe I'll put it one more across to give myself a little bit more room. Then we need a flipping jack socket. Now it's getting exciting because I know what's going to happen now is, oh, I don't know, it might fit, it might just go in. That'd be awesome. I thought I was going to have to be soldering some bits of wire on the end, which I don't mind doing. It's just that I thought that if I do that, I'm going to have to be desoldering them later, which is going to, and I'm going to make a right hash of it. So this fella, this seems to be going. I wonder if it will just plug in. I think it might. I think it just plugged in. That's just awesome. Oh, I'm so pleased about that. So the springy leg out the front, I think, goes on its own up this end, and the other side goes alongside this wire there. I mean, you can see the diagram. I don't really need to explain it every time. And then this connects also to that negative rail, and then we can talk about this second negative rail business. Okay, so that looks to me like that's all plugged in. Any other connections that I've made a hash of? No, that seems right. So, okay, so what were we saying about this here negative rail then? Moritz was saying about how this is not designed for dual power, and that's what we're using. So there's some kind of kind of hash going on. So I'm just going to plug these batteries into here, so that I am at least ready to go. Try not to stick one in my mouth. Okay. It's supposed to be hard and educational. Yeah, no, I can appreciate that. I can appreciate that. Yeah, Stan, definitely. Putting components onto a PCB from a BOM is just a soldering exercise. You're not learning anything. I think my point about the BOM is it allows me to confirm what things are. Otherwise, you get as a beginner, as I'm a perpetual beginner at this sort of thing, it feels like you're never certain, you're never sure, because you don't have a teacher to reach out to say, "Is this right? Have I got this right?" You have no way of confirming things. If you have a bill of materials, you can at the very least see that you've got the right number of components and see what their values are supposed to be. And that allows you to match things up and just gives you the confidence to know that the bits you are choosing and what you are doing could be right. Currently, I don't have any of that information. So I'm having to measure things, I'm having to Google things, and and that does have has its educational worth, but it requires a fair bit of determination to do that. And I think if you make it too hard, if you withhold too much information, people are just going to find it dispiriting and difficult, and not want to keep it going. I mean, that's just my thought on it. I mean, the battery thing here is a great example of that. I have very low confidence as to knowing what it is that I'm doing, even though I have watched the video on how to do it, but I've only watched it just the once. I haven't spent a long time on it, and kind of what I'm trying to do this evening is try to emulate a beginner's approach and situation in this, to see how easy it is to get over these sorts of hurdles. So I'm stuck with two batteries and my breadboard. I know that I've got a positive and a negative, and I could plug that into positive and negative, but there's something else going on that's not explained particularly well. So no, I mean, it's explained brilliantly well. It's explained at a level which is not translating to the physical connections of this to the board. So let's see if we can get around that now. Right, let's go back up to what the diagram on the battery. Let's do that bit. So we've got two batteries, and I know that I'm going to connect the negative of one to -9. It's -9. The negative one goes somewhere. The positive goes to the same place as the negative of the other one, and then the positive goes somewhere. So I'm ending up creating 3 rails. That's the point, I think. Okay, so in that respect, when we're talking about this breadboard, if we're creating 3 rails, and we've already talked about the resistor going to ground, which is this line here. Although it's labelled negative, we know that that's supposed to be ground, which is supposed to be 0 ultimately. So this blue negative one here needs to be 0. This positive red one here can be +9. Is anything going to it? Yeah. Can be +9 volts. And maybe when he's pointing to this bottom row, he's meaning that this bottom plus one is actually going to be -9. Have I got that right, people in the chat? While I just go up again. So two batteries, breadboard. Yes, says Moritz. Good. Okay. Yes, 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 yes. Okay. So what was it that I said? So I do have stuff here that's also connected to the negative rail at the top. But anyway, so I'm struggling to keep this in my head. So positive. So I want positive on one battery, which is this red one, to go into the positive rail there. The negative needs to share. I mean, is it going to be, if I put one of these in, is that going to be a problem until I put the other one in? That it's actually going to be... Oh. I'm overthinking it, I'm sure. So this one goes into this one. It's hardly got a bloody end on it. Okay. And that goes along with the positive of this one. And this goes into there. So what is it that goes into this top rail? Is that right? That's right, I think. This is exactly the stage you find you want. Not yet. What? What not yet? Now just jumper, negative to negative. Do you mean -9 or 0? Yeah. So I've got a jumper. So are you saying the -9 rail, the ground one? So is that one ground? The ground one, blue to blue. So not negative to negative then. Oh dear, that's funny. Well, it's sort of funny. Negative to negative. Boom. Okay. Clock's ticking. Core flip me. Look, it's nearly 20 to 10. The black lead from the second battery should be connected to the top rail. No, it shouldn't. Anyway. Okay, blue to blue. Good. So at this point, as we understand it, it is oscillating and we should be getting a sound. Should we check that? Oh my goodness. All right, so hang on. I need to get a bit of cable. Now I had this sorted out somewhere. Is this going to reach? Now, it's... I tend to get a little bit sort of twitchy around electricity, like I'm going to hurt myself. I don't mean to be. I'm just going to plug that in there. Oh, that's a high-pitched noise. Can you hear that? It is that. Okay, we're getting an oscillation. A high-pitched oscillation, but an oscillation nonetheless. Look at that. Cool flip. Yeah. So yeah, no, that was a little high, but that's there we go. So, is it possible for me to recap what has occurred by way of attempting to stick this stuff in my head? So we use a Smith trigger, which generates current, which fills up a capacitor. It then turns off at that point, So the capacitor can then release, which gives us our sawtooth wave. Then something to do with an op-amp, an AC coupling. This bit over here is removing an offset so that we don't like plug it in, and so you don't get a flat voltage which could damage your speakers. That's what DC offset tends to do in an audio signal. Obviously you want that if you're using control voltages, but we're not. We're talking about audio. I can still hear that high-pitched thing, which doesn't seem right. No, I can't hear it. The board. Anyway, the op-amp, oh yeah, the op-amp is creating a buffer which kind of is, without interfering with the circuit, is measuring that voltage change in a sort of an isolated way. So it's buffering that oscillation without affecting it. Unlike if I'd plugged the audio thing straight in, then the signal just would have gone straight through it and it wouldn't have been filling the capacitor because it's easier to go this way. Whereas the op-amp buffer is measuring that oscillation without interfering with it. I don't understand quite exactly how it does that, but that's by the by. That's what it does, and that's bringing the signal over here through the AC coupling to remove any offset so that it's nicely oscillating around 0. That gives us our waveform output. Oh yeah. Yes. Oh, I wish I'd brought the beer now. Right, what's next? Now I don't have an oscilloscope to hand. I do have an O'Toole in my rack, but it's not particularly accessible right now, and it would just be a whole waste of time. We understand, we heard the signal, yeah? So we know that something occurred. We don't need to see it. One of these days I'll get like a proper oscilloscope, and then the next time I'll know how to actually use it. So very high pitched tone. Yes, that's what we got. Good. Right. Bit more learning coming up. Changing the frequency. See this, okay, this could get interesting because we might start swapping capacitors. Okay. So let's talk about changing the oscillator's frequency. Remember when I said there's a sawtooth wave's pitch is easy to manipulate because it's solely dependent on the wave's second phase. Yeah, okay, it's the drop away from the capacitor which lengthens that decay, which essentially lengthens the waveform, which reduces the frequency because it's become longer. Its wavelength has increased, which reduces the frequency, which makes the pitch lower. Oh, I'm really on it now. So if it's discharging fast, the pitch is high. If it's discharging slow, the pitch is low. Speed of the discharge process is determined by exactly 2 factors: capacitor size and resistor strength. Bigger the balloon, more water it can store, the longer it takes. Tighter the drain, the more it restricts the amount that can flow. Right. Let's try this out by swapping the 2.2 nanofarad capacitor for a 1 farad one. I don't know what that is. So capacitors wise, I don't have another film one. I have these, whatever they may be, and I've got the 104s, which I can't remember what they are. So anyone in the chat know which one I should swap out that one for? Yeah, I know I can swap the resistor. That's reading ahead, that is. We'll come to that. We'll come to that in a minute. Okay. You should be able to hear the frequency is a lot lower. Just use a ceramic. They are thermistors. Oh, are they? Okay, cool. Cool. Thanks for that. Good to know. Those are thermistors, I'm now told. Cool, yeah. Okay, people are suggesting I can use one of the 104s, which is these, which are 100 nanofarad. So it won't go quite so low, I think. Okay, cool, cool. Yeah, gotcha. So, again, I'm just going to pull it out. Should I be taking the battery out first? Too late. You should have got in there sooner. So this goes between the pin with the resistor and that end pin that goes in between. So this is pin 7 and 5. Okay, so I'll put that in. There's the thing. The pitch should be lower. Oh, look at that! Look at that! Right, I could actually leave that running. So that's not so bad. I'm making oscillations on a breadboard. Oh, okay, super. Then you want to swap your the resistor for a 1 meg one. I've got a 1 meg one here, I think. Is that also a 1 meg one? I think so. They look the same? No. They don't look the same. I think that was a 1 meg. Anyway, let's try this one out. What's the worst that could happen at this point? So now we are changing the resistance. Okay, I break the connection. It all just ceases to function. Nice. So I've put in a different resistor. Higher resistance, lower pitch. I can imagine at some point we're going to use a variable resistor, right? See? I think so. Right, so we did that. So which route do we take? Changing the capacitance or changing the resistance? Well, it's pretty much a non-choice because changing the capacitor can only be done manually. Well, what about a flux capacitor? Anyway, by taking the old one out and installing a new one. And it's not the most fun way to make music. I don't know, I've seen synthesizers that come with capacitors that you jam into things. Which leaves us with one option, changing the resistance value. We thankfully have more options than just changing it by hand. We could use a light dependent resistor, good one, where the resistance depends on the amount of light that shines on it. We could use a thermistor, which is the same idea, reacting to temperature. The classic idea would be to use a transistor as a constant current sink. OR. Transistors are uniquely qualified here because the relation between the voltage applied to their base and the current they allow to flow between collector and emitter is exponential. And that's important because musical notes and their assigned frequencies is exponential. Because you have frequency doubling, it doesn't go up by the same amount, it doubles every time for every octave. So since we're trying to make our VCO conform to a 1 volt per octave standard, we want to match voltages and frequencies like this. Whenever the voltage increases by 1, our oscillator's pitch should go up an octave. Yes. The relationship between voltage input and frequency output needs to be exponential to achieve this, because we're basically mapping voltages to musical notes. Yes. Because our oscillator's pitch is determined by how our transistor is, it's crucial that the transistor opens up exponentially as the voltage at its base increases linearly. Okay. Well, I wasn't expecting a transistor, I was expecting a variable resistor, because isn't that what would happen? I mean, if I was to stick another resistor into those same holes, like that, then I'm changing the pitch, yeah? All right, now we're talking. Now we're talking. Okay, cool. Right, so yeah, we kind of got that. Good. So now we're talking about some kind of transistor. Interesting. So I can leave that plugged in. I'll just turn it down. There we go. One meg versus finger. What? Right, okay, anyway. So, don't try this at home, kids, and all that sort of thing. So what did we get to? So we've got some business with a transistor, which we have in this diagram here. So this transistor operates in the place of the resistor. See, I was not expecting that. Okay. So let me read again why we would use that. Transistor as a constant current sink. Well, a transistor allows current to flow through that leg and then out of the arrow when there's a voltage across the, or a current, I can't remember which, voltage across the back. It sort of acts as a switch. The relation between the voltage applied to the base and the current they allow to flow. Okay. So a transistor, in this instance, controls the flow of current through itself by the amount of voltage behind it. So if you vary that voltage, that varies the current going through it exponentially. Okay. Maybe that's what a variable resistor is. I don't know. Anyway, stop talking, otherwise you make yourself seem silly. Okay. So it says enough theory, right? Let's see if any of this works in real life. Right, so replace our drain resistor. Okay, drain resistor. Gotcha. So that's 100 watts. This is a boom 1 meg thing. Should I put the... No, I don't. I think... Oh, we'll leave it for the minute. I won't change the capacitor back just yet. So we're going to replace it with a transistor. Now I've got two 3-legged things. Let me just check that they're the same. What did I do with my head things? Are they on my head? No, oh, they're here. Okay, right. So these things here. That's a CTBC 548C, yep. That's a 548 and a 558. Which one do I need? 548. I'll put that there for the minute then. So I've got a 548. It's just a standard general purpose NPN variant. Okay, got to connect the collector to the junction of the capacitor and diode. Yeah, well, the emitter needs to link directly to ground. So looking at it this way round, the flat front on it, the left-hand one is the collector, base, emitter. So the collector, what happens to the base? Right, I think I need to look at the layout below to understand how that's exactly going together. Okay, so I just had a little realization, which is that when I keep talking about a variable resistor, I don't really know what I'm talking about. I kind of think I do, because I see pots as a variable resistor, because that's kind of how you imagine the world to be. So what do I mean? I mean, I'm imagining that when I turn this, I'm increasing the resistance or decreasing the resistance, and that's changing something. And that's actually nonsense, because this is a potentiometer, and these are used as variable voltage dividers. In other words, it outputs a voltage, not a resistance. Am I understanding that right? Cool, well, anyway, let's not get hung up. Come to that in a minute. So to vary the voltage at the base, we're using a potentiometer, which is a variable voltage divider. It allows you to dial in any voltage that you want. Okay. For it to work, we'll set up a 100k potentiometer as shown on the breadboard while connecting the wiper. What's a wiper? To the transistor's base through a 100k resistor. This will limit the maximum amount of current going through the transistor, preventing it from going up in flames. Cool, yeah, well, that's a good positive thing, I think. So let's have a look. Now we're going to have problems. Are we going to have problems? No, not necessarily. Right. So in order to connect to that, I don't have a spare. Do I? Oh, there's a spare there. Something has changed. I've taken the resistor out. Okay, let's take that out for a minute. So we've removed the 100k resistor because that's no longer going to be there. Gotcha. Right. Okay. Removed that. Now they've just moved around on the breadboard. Some of the components have moved around because, does that matter? Trying to suss this out. They've moved the diode to the other side to fit in there, here. I think just because it's neater, not because it's doing anything. So I'm going to pull that out of there, put it in here. So I've just shuffled it down this strip. Those are all connected, and it all still remains the same. I've just moved that over there because that resistor is no longer there. So I have space now to put that diode that has come out. Where's that? Is that going to cause things to break? Let's hope not. So we take a wire out in order to allow us to do some more shenanigans. And it goes from where all three of them match up. So that one, they are all in this one here. So that one, we're bringing that out over here. somewhere to give us a bit of room. Not too far. We're then using the 100k resistor. No, we're not. We're using this fella first. Now this, it's got 3 prongs, so I'm assuming it goes into three things, and the middle one is the base, and the middle one is taking the 100k over to the pot. So this needs to have one leg attached. Now that leg is the collector, I think. Let me go back up. Come on, brain. Come on, brain. Collector to the junction. So the collector is the one when I'm facing it on the left. So when it's up that way round, it's the one on the right. So this is the one on the right, which goes there. So I should just be able to put all 3 legs in together, facing that way. Then I take a 100k resistor, which came out previously, which was our drain resistor, which is what we heard it was supposedly called, and that goes into the middle leg and across that center thing from the middle leg. Middle leg, yes, middle leg. Somehow I've got to put a pot in. Doesn't really say anything about that pot. Now, I've got, I mean, could it be, are we talking about this one, the little squidgy blue one? Cheers, Bill. What is called not a knob? Yeah, well, if people do have to shoot off because it is 10 o'clock, that's fine. Like I say, I think we might revisit this on Wednesday. I will attempt to get to the end of the breadboarding this evening, because there's no point trying to solder at 12 o'clock at night. So yeah, thanks for stopping in. We'll keep on going. We'll keep on going to the end of the breadboard section, I think. I'll see you in a minute. But we'll do the soldering next Wednesday, and I'll have a rethink about how I do this for the next one. Whether it's worth doing it in 2 sessions like this, I don't know. I'll be really interested to know how you felt, whether this was a car crash or whether this was useful. All those sorts of things are really helpful for you to put in the comments, so that I can make this as useful, helpful to people as humanly possible. So I'm not just sort of here for my entertainment, for my own ego. Anyway, so hang on. Right, so the pot, it talks about a 100k potentiometer. I have 2 choices of what I recognize as a pot. One is I would see this as a trimmer, but I guess it's the same thing, really. And this is what I would consider to be a pot. Now in the picture on the screen, it's kind of a bit boxy, but then they are a bit boxy. And it looks more like this one than this one to some degree, but then this has got its little turny bit on the corner. This has its turny bit in the middle, and it has its turny bit in the middle on the screen. So I'm just going to have a look a little bit deeper. Let me have a look. Is anything written on these fellas? Well, B104, whatever the heck that means. This one. W102. not telling me anything. Thanks, Tonal. It says no. Moritz says no. Bend the legs of the pot. It says so in the footnote. Right, okay. Okay, so for that to work, we'll simply set up a 100K potentiometer as shown in the breadboard layout below with footnote number 4. Let's go down and check that out. If the pot doesn't quite fit, try bending the legs upward a bit. No worries, this won't break it. No, that doesn't. Are we? I mean, are we talking about this? Is this what we're talking about? And do you mean just sort of pushing it like that so that it fits, so I don't have to worry about these lugs? I think that's what you mean. Does it matter which way round it goes? I might just plug it in and see what happens. So this goes in the middle 3. Oh, you need to have a little bit of room. Yeah, they're a bit fat, but I think they're going in. That's the pot. Yes. No, says no. That's the pot. Yes, yes, yes. No. Yes. Big pot. Yes. Oh, confidence is high. Confidence is high. Let's try a few more of these cables. Get through a lot of these buggers. Right. So, meanwhile, this far one here, which I can no longer see, I have to bend that a little bit more. So this leg there, that goes to this far end one, and this number 3 leg goes to this middle one. So I can't see my transistor anymore, but it's in there. I promise you it's in there underneath the pot. Okay, nothing's gone up in flames so far, but then as my battery's still connected. No, of course they're not. So that keeps falling out. So that needs to go. No, not one there. That used to go in there. And in there. Okay, still no smoke. Good sign. Right. So what should be happening is we fiddle with the knob and you should hear oscillator seem completely dead in the upper range. Then it becomes audible. Right, so we'll plug it back in. That's either very high or okay, nothing at the minute. But that could be for all sorts of things falling out type reasons. Okay, there should be something happening. Just going to check back through what we're looking at, because it did get a bit crowded and silly in here. What if I have that connected? Middle leg, first leg, going into there. missing anything else? Anything else new gone in to there? Now it may be because I've swapped out the capacitor. That could be a... Oh, that could be... No, that's just come out of there. That could be a factor. Now, my money's on the pot. Oh, pulled it out. You're missing the emitter ground connection. Ooh, do you think? Oh, I am. Yes, thank you. I am. I am missing that connection. Oh, I've lost power. The battery's on hot. Fabulous. Look at that. Who would have believed it? God, flipping heck. Wow. Okay. You know we're only on page 13, right? Yeah, I'm gonna have to make a decision to stop at some point. Now, okay, so once we've set this up, try fiddling with the knob. Yeah, did that. So yeah, it's swinging about a bit too much. As soon as you get down to something, it becomes audible. Yeah. The range is roughly between 350 and 550 millivolts. Also, I do have the wrong capacitor in at the moment. So it's going to be a little bit different to that, perhaps. Aren't we going to run into trouble if we connect a sequencer? Okay. But if the usable voltage range of the transistor is only between 350 and 550 millivolts, have I missed something here? As you hear, our oscillator seems completely dead in the upper voltage range. Yeah. Well, there's only a little range. Quite a fun experience, Ooh. Nice. Yes, lovely. Right, so so essentially we're getting a very small range of pitch change. And we want our VCO to conform to a standard. So starting with 0 volts, every volt should span exactly 1 octave. Yes, we're not getting that yet. So there has to be something that makes that happen. So the next section talks about sequences, scaling and offsets. Spanning 5 volts, 5 octaves. And and marked the usable range of our transistor. So we've only got this tiny little, the dotted lines are the usable range that we've got, comparing it with an actual sequence that you would get from Eurorack. So yeah, it ain't working quite right yet. So yes. So to fix these problems, we'll deal first with the size or voltage range. Okay, I'm going to skip ahead a little bit just to see what we have left to do, because I think this is going to go on for too long. Oh, right. Flipping heck, we're going to actually connect a sequencer. That's very exciting. So there's a bit there to connect a sequencer. Then we're going to have a look at some temperature troubles. Then there's tuning. Okay. Well, okay, I think perhaps what we'll do at this point, I think we should probably stop. Because I think it's a good place to stop, the fact that we've got a variable pitch out of the thing. Now, I understand that it's nowhere close to becoming a VCO that we want, but I love the way that this is building up on this breadboard. It's just amazing. I mean, it's boggling my mind, but it's fascinating, and I've flipping learned so much already about how an oscillator works. You know, top job, Lawrence. It's just fantastic. This is exactly what I needed, exactly what people need, I think, if they want to dig in a little bit further. Because as I've said many times, I can easily build a module from a kit without any bother. But this is really, really, really fascinating. So here's what we're going to do. I'm going to have to make a decision. I knew there was a reason why next Wednesday was free. So what I would like, if you've been building along, I'd like you to go away and between now and Wednesday, follow the next stages through. I'll do the same. If I can, when I do it at some point next week, I'm going to have to squeeze it in somewhere. I'll try to live stream it, but I won't necessarily be able to do that. But what I would like anyone who's building along to do is to work through the rest of the guide up to the point that you have a fully breadboarded VCO. Yeah, so that's your homework. That's your homework for Wednesday. Maybe that's how this is going to work. Yeah. So we'll do that. I'll work through it as well. And so next Wednesday we'll get together 8 o'clock, and we should be at the stage where we have a completed VCO on our breadboard, and from there we'll then punt into the soldering and build the thing as a module and test it in a bit of Eurorackness. So we haven't done a single bit of soldering tonight, but we have built a sawtooth VCO, which is extraordinary, just totally extraordinary. With a few hiccups along the way, but I've been very, very grateful to the chat. Very great to you, Moritz, for being in there, helping me along. That's been invaluable. Yeah, figuring it out. That's kind of what it is. That's what it is. Interesting. Oh, that's funny. So, what am I doing? Who am I doing it with? What am I trying to do? Oh yeah, I was going to go here. And what's that one? That's number 5. What am I? I'm number 2. Am I? I think. Yeah. Okay. So there we are. Right. So yes. So that's the plan. Then next Wednesday, will be the return of the Erica Synths VCO, getting properly soldered together. That's what we're going to do. So do your homework, bring your breadboard as it was, or just come along to watch and see how we did. Hopefully I'll get through the rest of this without like melting my brain. And if I can turn the cameras on when I do, I will. If not, I'll just tell you about it on the Wednesday, and I'll talk you through where I got to and the tricky bits that I encountered along the way. There we go. That'll do. That's a Friday night. So coming up next week, then we have Noir A Blanc V on Monday night. Stephen, who has left Eurorack, sort of, kind of, almost, and we're going to chat to him about his journey through Eurorack, because I think when I started in Eurorack, I hadn't been doing it very long. I just started making videos, and then Stephen came along, and it was like, oh, there's no way that I can make videos as beautiful as that. But there seemed to be room for both of us. So he was making beautiful videos about Eurorack. I was making kind of crappy videos about Eurorack. But, you know, it's all good. It's all good. And it's been interesting to watch his journey through that. And then recently, at some point last year, he started talking about how he's kind of had enough of it and wants to go back to proper synthesizers. So we're going to talk all about that, how that happened, and what his thoughts are on Eurorack. Where does that take him now? And is it food for thought for the rest of us, or are we going to be sitting there going, no? Which is, I don't know. I mean, I think both of these ideas can totally exist in one space. So it'll be interesting to talk about that. Tuesday, I'm talking to Philip from Modal Electronics, just about the argons, the cobalts, and synthesizers, that kind of thing. So that'll be cool. So Wednesday night, we're going to come and solder this bugger together and get it to work properly. That'll be very, very cool. Thursday night is Seat Your Pants, Hair on Fire, live performance in Gringos in Norwich on Thursday, which I'm going to attempt to live stream through my phone. I don't know whether that's going to work, but we'll give it a go. All right, that's Thursday. And then Friday night, we'll just get together, have a beer, and talk about how it all went, because it will by that point have been a mad couple of weeks. So there you go. That's the plan. So thank you very much for joining us. And of course, if you're watching this later as part of the Erica Synths, my series on building all the modules that I'm talking about this couple of weeks, I've done a whole series of live streams on different things and different subjects. But the rest of the Erica Synths ones will be individual by themselves as the modules come out, and it looks like we might be following a similar format where we have one session on the breadboard and another session on the soldering. Maybe that's the best way to do it. We shall see. We shall see how this one goes on Wednesday. So thanks for joining me. That's been brilliant. That'll do. Yeah, I'll go and have a good weekend. Go make some tunes, and I'll see you soon. Let me find my outro music.